Dear students of plus 2 medical and non-medical and their respective teachers, today I am going to discuss electric potential due to a dipole at a point on axial line, at a point on equatorial line, and I will also drive relation between electric field and potential gradient. So let us start. Electric potential due to dipole at a point on axial line. So suppose AB be the dipole having minus q and plus q charges at A and B respectively. O be the center of dipole. 2L is the length of the dipole. Let OX be the axial line. Then let P be any point at a distance r from the center of dipole where electric potential due to dipole is to be determined. So let OP is equal to R, then BP will be equal to R minus L. AP will be equal to R plus L. Very simple. Then by definition of electric potential due to a point charge, V is given by 1 upon 4 pi epsilon naught Q upon distance. So V is equal to 1 over 4 pi epsilon naught constant Q over BP minus Q over AP, because electric potential is algebraically added, or Q can be taken common. Q upon 4 pi epsilon naught. What is BP? 1 R minus L. So 1 upon R minus L minus 1 upon R plus L. Thus the values of BP and AP. Or simplifying it, we have R square minus L square in the denominator. Q upon 4 pi epsilon naught. R plus L minus R minus L means minus R plus L. So R cancels. So this 2L into Q into L is P, electric dipole moment. So V is equal to 1 over 4 pi epsilon naught P upon R square minus L square whole square, which is the required expression for electric potential due to dipole at a point on the axial line. So very simple. When L square is negligible, as L is less than R, when point is far away from the center of dipole, and for a short dipole you can say L is less than R, or L square can be neglected. Then V comes out to be 1 upon 4 pi epsilon naught P upon R square. It means electric potential due to dipole is inversely proportional to square of the distance for the point from the center of the dipole. Next, equatorial line. Suppose again we have a dipole AB having charge minus Q plus Q at A and B respectively. O is the center of dipole, 2L is the length of dipole, OY is the equatorial line, that is perpendicular bisector of the dipole. Then let OP is equal to R, then this BP is equal to AP will be equal to 1 root R square plus L square. That is, in this case BP is equal to AP. So V is given by 1 over 4 pi epsilon naught. Again same formula, Q upon BP minus Q upon AP. Now Q can be taken outside, or you can say BP is equal to AP. As BP is equal to AP, this cancels. So V is equal to 0. It's very important. It means electric potential due to a dipole at a point on the equatorial line, at any point on the equatorial line, is always 0 because of symmetry. So electric potential due to dipole at a point on the equatorial line is always 0. Third, we have to reduce relation between electric field and potential gradient. Now suppose Q be a point charge lying at point O. Let OX be the x-axis, you can say. Let A and B be the 2 points. Then electric field at A due to charge at O will be along this AX, or along OX you can see. Let the test charge plus 1 coulomb, positive test charge, is moved from A to B through small displacement dx. Then electric field vector and displacement vector dx are opposite. That is, angle between E vector and dx vector is 180 degree. So then amount of work done, small amount of work done in displacing the test charge plus 1 coulomb from A to B through small displacement dx, dw is given by f dot dx, but charge is plus 1 coulomb, so it will be E dot dx, because f is equal to qe. If q is 1 unit, so it will be E dot dx, or minus E dx, because theta between E and dx is 180, so cos 180 is minus 1, so it will be minus E dx. So this is equation number 1. Okay. So this is because work has to be done in order to move a test charge of plus 1 coulomb in an electric field of given charge q. That's why this work done comes out to be minus E dx. Also, by definition of potential difference, it is defined as amount of work done in moving a unit of positive test charge from one point to another point. So dw will be equal to dv. dv is the potential difference between A and B. Then 1 and 2 must be equal. So dv is equal to minus E dx, or E is equal to minus dv by dx. So very important relation, that electric field is equal to negative gradient of potential. So electric field is equal to negative gradient of potential. So you can say, in other words, electric field is equal to V upon D sometimes. Potential difference per unit distance. So SI unit of electric field can also written as volt per meter, because SI unit of potential is V, distance meters, volt per meter, or Newton per coulomb by another definition. So this is all about electric potential due to dipole at a point on axial line, equatorial line, and relation between electric field and potential gradient. So very simple, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਤੁਹਾਨੂੰ ਸਾਰਾ ਸਮਝ ਆ ਗਿਆ ਹੋਊਗਾ। ਤੁਸੀਂ ਇਹਦਾ ਸਕਰੀਨਸ਼ਾਟ ਲੈ ਕੇ ਦੁਬਾਰਾ ਸਟੱਡੀ ਕਰ ਸਕਦੇ ਹੋ। ਤੁਸੀਂ ਇਹਨੂੰ ਆਪਣੇ ਟੀਵੀ ਤੇ ਨਾਲ ਵੀ ਅਟੈਚ ਕਰਕੇ ਇਹਨੂੰ ਮੈਗਨੀਫਾਈ ਕਰਕੇ ਇਹਨੂੰ ਦੇਖ ਸਕਦੇ ਹੋ। ਸੋ ਐਵਰੀ ਸਟੈਪ ਇਜ਼ ਵੈਰੀ ਕਲੀਅਰ। ਸੋ ਟੂ ਸੇਵ ਟਾਈਮ ਆਈ write before making video. So thank you, all the best, be happy, good luck.